Okay. All right, we'll get started. Let's do our recap so that we can finish basic structure and then move on to the third topic, protein analysis. Okay, so how do we determine the isoelectric point of a neutral amino acid? That means the amino acid, the R group of the amino acid does not have ionizable. Yes. Okay, so the pKa of the acidic group plus the pKa of the basic group divided by 2, you get the isoelectric point. What about the acidic amino acid? So the acidic, you'll take the pKa of the carboxyl group and then the pKa of the other carboxyl group in the R chain, and you divide by 2. For the basic, you take the pKa of the basic group, the amine group, plus the pKa of the amine group in the R chain, and you divide by 2. Okay. All right, so let's give examples of functional groups in the R chain and some reactions they could be involved in. Huh? Sulfhydryl group and disulfide. Very good. What else can you think of or remember? Huh? The aromatic gradients, what kind of interaction they might have? Hydrophobic interactions, they also absorb light. So that's good. What else? Do you remember? OH. Like say. Oh yeah, so the OH group in serine and threonine. So serine can be phosphorylated and threonine can be glycosylated. Okay, what about lysine? What's in there that is reactive? Related to your research. Primary and yeah. So that it will react, it's most reactive in the Maillard reaction. Okay. So yeah, so these are just few examples. That you would want to remember as you do your work on your flashcards. Remember your R groups. So remember the functional groups and what potential reactions. Okay. Okay, so do you remember we talked about the role of hydrophobic residues? Do you remember in the folding, what happens? When in the cell you have the amino acid chain. And then what happens? The hydrophobic residues in this chain, how do they play a role in folding? Huh? Yeah, but in the folding, because induces folding. Induces folding because they want to interact with each other. They don't want to interact with water. So they start hiding from water and then they bring those residues within the chain, they bring them closer to each other. And that brings us to the fourth question. What are main forces stabilizing protein secondary structure? So that initial movement and start of folding brings the residues close to each other, and what type of bonding occurs? Hydrogen bonding. Okay. What about tertiary structure? What forces stabilize tertiary structure? Hmm? Disulfide bond is one of them, but there are other electrostatic. So disulfide are the only covalent bond that stabilize tertiary structure. Other than covalent, we have electrostatic, hydrogen bonding, hydrophobic interactions, van der Waals. Although they're weak, but they're adequate. So yeah, all sorts of non-covalent interaction contribute to the stability. So if you want to remember the the free energy concept, when you form that polypeptide, there's a lot of stretching and bending and a lot of energy, and the protein starts to fold to form interaction to contain that energy in bonds. Yeah, speaking of containing energy and free energy, what's enthalpy? Welcome. What's enthalpy or entropy in simple terms?
Entropy is just disorder.
Disorder, chaos, a lot of energy.
And enthalpy, the heat, amount of heat needed or released. I guess when.
Okay, so it needed release. You're getting there. So it's the amount of energy or heat contained, and of course, the same amount of energy is needed to break those bonds. Like, when we do the SC measurements, we're going to talk about it in the next topic. So when we do the SC measurements, we give heat in our little pan to put samples and put them in a compartment and start giving heat. So when enough heat is given to cause denaturation, we see that endothermic heat, and we calculate the area under the curve, which is the enthalpy or the energy needed to cause that denaturation to break down the bonds. Okay, so entropy is disorder, chaos. Enthalpy is the containment of the energy in bonds. Okay, so what could disrupt hydrogen bonding? What could disrupt? You use it, those of you for gel electrophoresis, what do you put? SDS. So SDS it's a detergent. So detergents can break hydrogen bonding. Detergent can also break hydrophobic interactions. Urea can also break hydrogen bonding, hydrophobic interactions. So heat can disrupt hydrogen bonding, but strengthen hydrophobic interaction. So what can disrupt disulfide entities? What do you add? DME, yeah, or D2P. So reducing H. So you reduce the disulfide linkages. Okay, what could disrupt ionic interaction? Ionic strength, so salt. So can shield charges, by shielding charges can disrupt positive and negative interaction with each other, or can cause repulsive interactions. That means they same charges will repel each other, so can break bonds by forming repulsive interaction. What other than salt? What's that? So hydrophobic interaction, detergent as well, and urea can break it. And cold, temperature, low temperature. Yeah, so other than ionic strength, what can disrupt ionic interaction? You do that in the lab, you change what? pH. Yeah. Okay, very good. I think we covered that one, how does the free energy concept when you have a lot of stretching and bending of bonds, a lot of free energy, a lot of chaos, a lot of movement, and then bonding occurs to kind of contain some of that energy in bonds to reach the most stable state. So when we denature the protein, this is one of the questions you have in your practice problems. So delta G will be negative. So that negative delta G is leads to spontaneous denaturation because you're breaking two bonds, you increase the chaos, the movement, and then delta S will go up, then delta G will be negative. So that'll be spontaneous denaturation. But after you denature the protein, after the protein is denatured, it will have to form a stable form again. So it would be denatured, but then it will have to go into another stable form. So that form is stable, but not as the original nature. So it will have to contain the energy either by forming new bonds within the protein or bonds with another protein next to it in the environment. So that free energy would have to be contained, but we already denatured that protein. Okay, any questions? All right. So we can continue where we left off. So we talked about primary structure and we talked about folding. Now I'm going to talk about the different types of secondary structure. So after formation of the primary structure, which is the amino acid composite sequence, putting those amino acids in sequence, then the protein starts to fold. Depending on the sequence of the protein, we would get different forms of secondary structure. So a very common form is your alpha helix, the beta sheet, that beta turn, the arrow here, I guess, the beta turn, and then all of these non-conformational shapes, we call them random coil. So these are the different forms of the secondary structure. And like I said, the native secondary structure depends on the sequence and size and the composition of amino acids. Okay, College Bowl type questions coming up here. So alpha helix, the sequence of amino acids that would potentially form that shape, P is for polar, N for nonpolar. So if you have a sequence of amino acids, polar, nonpolar, and two polars, two nonpolars, and the sequence repeats, that would potentially form an alpha helix. Of course, there is, not always follows the rule, but that is in general the rule to form an alpha helix. And then in one turn, that is a College Bowl question. In one turn, you have 3.6 residues. That means 3.6 amino acid molecules in a turn. So the interior is occupied mostly by hydrophobic groups, and the exterior mostly by hydrophilic. Now, hydrogen bonds stabilize that alpha helix structure, and the hydrogen bonds form parallel to the axis. So this is the axis. Hydrogen bonds are forming between the different residues parallel to the axis in an alpha helix. So remember, proline will disrupt alpha helix. Even though you would have that sequence, doesn't matter. If in that sequence you have proline, you have steric hindrance because of the covalent linkage of the R group to the N. So there's not much movement, so not much bending. So proline is a secondary structure disruptor. Beta sheet, easier to remember, polar, nonpolar sequence. But the way it forms between two strands within the one polypeptide. So what does that mean? Is there light for this? Is there light for the board, do you think? To line the board. So what that means is like if you have one molecule, so if you have this kind of shape, you can form here hydrogen bonds. So between two strands within one molecule. That's what it means. And then the hydrogen bond forms perpendicular to the axis. So this is the axis and hydrogen bonds form that way, perpendicular. Beta turn, it might exist naturally, but also it can increase, for example, in dough. When we are kneading the dough, we can generate more beta turns. So this can happen as part of denaturation. So reversal of beta sheet, and then you get this turn between two beta sheets formation. So that's beta sheet. Random coil is random coil, doesn't have a specific sequence. It just does not, the sequence for it does not fall under beta sheet or beta turn or alpha helix. So it would be random shape. Now, what you see here is two different types of proteins. One of them has a lot of alpha helix, and maybe just minimal beta sheet, if any. Whereas the other one, beta-lactoglobulin, has a lot of beta sheet and one alpha helix. So the secondary structure impacts temperature, denaturation temperature. So beta sheet is more stable to thermal denaturation than alpha helix. So because of that, you can see that beta sheet denatures at 75 degrees C, whereas alpha lactalbumin can denature at lower temperature, 64. So alpha helix is more prone to denature than beta sheet. And presence of beta sheets actually correlate to good gelling functionality because it has better, it's more stable and gives more strength to the gel. And also beta sheet in dough formation can also stabilize the dough after the dough rises, and when you put it in the oven, it keeps the volume. So this is very unique for gluten proteins in wheat. But if we try to do bread with corn, they have less beta sheet formation. So the dough, although it might rise, it will collapse upon baking. So those beta sheet play an important role in functionality of the protein, and also there are an indication of denaturation at the secondary level of the protein. So the denaturation can be at the tertiary level, a secondary level, and a primary. So you can have denaturation at the secondary level, and you would see, compared to a native protein, you might have more beta sheet and less alpha helix, or more random coil will increase. The proportion of random coil will increase in a. So oftentimes when measuring denaturation or the level of denaturation at the secondary level of the protein, we calculate ratio of alpha helix to beta sheet. When this ratio goes down, that's an indication that the protein denatured not only at the tertiary level, but at the secondary level. Another thing will happen is after thermal treatment, some of the alpha helixes present will convert, will unfold, and then the protein, when it rearranges to form a stable structure, you might get more beta sheet formation. So this we can notice in some example later on. I will give you examples when we cover thermal denaturation. Yeah, but that's what would happen normally when we look at secondary structure. We look at how did the beta sheet change? Did we increase beta sheet? Did we increase random coil? And then we try to figure out the impact on functionality.
Even I see that automatically really more solid than
Yeah, more soluble.
yeah, because of the deficit and on high of the deficit.
Not necessarily. It has to do with what's on the surface of the fruit. The surface hydrophobicity and the charge of the fruit, not the beta sheet. The beta sheet would be indication of thermostability more than solubility. Also, in the presence of calcium, alpha helix gets more stabilized because alpha helix, alpha lactalbumin specifically, if you have calcium in the way they can form bridges, protein bridges in the presence of calcium and stabilize. Okay. The next level of the structure is tertiary structure. And we're going to talk about that. All sorts of bonding can happen to stabilize tertiary structure.
Could you upload the slides for this on?
It's under week 3. It should be
Oh, okay, it's just I guess.
yeah, I mean, I'm like always, I'm behind. So these are under week 3, and
Because it looks different on week 3.
it looks different.
I'm on week 2 and it's the same as this.
Oh, it's
So
on
week
week
2 slides are this.
Yeah. Okay.
What do I have on week 3?
No, it's like the last 30 slides or so are these ones, but the beginning is whatever we covered from before. It's like repeating slides. If you go down 36, I think it starts this. No.
7.
Yeah,
Sorry.
because I didn't finish. I was supposed to finish this last one. I didn't finish it.
That's what I thought. I just didn't know where we were. Sorry about
Oh, sorry. No, did I email you guys where we are? Or you can figure this out. Okay. All right, so when we form the secondary structure, the next level is stabilization through the formation of tertiary structure, because we still have a lot of energy, free energy going around. So the proteins continue folding and forming the bonds. So it could be hydrogen bond, not necessarily only in the alpha helix and beta sheet, but outside of that. Hydrophobic interactions, disulfide linkages, ionic bond, and also van der Waals, which are not depicted here, but they were in previous slides. So once your free energy is contained in bonds, then you get your stable tertiary structure. But some proteins are very hydrophobic on the surface. They have to form another stable form through quaternary structure. And we'll talk about quaternary structure in a minute. But tertiary is more stable than secondary structure. And there are different configuration for tertiary structure. You have the most common globular structure that is, folded on itself. And a unique structure for beta casein is the open, flexible structure. And the reason that caseins are open structure, again, is the protein, the high percentage of protein that is there that does not allow them to really fold on itself. So quaternary structures are formed due to many reasons. So plant proteins that have high degree of composition of non-polar amino acids, so which makes some of them on the surface. Not all of them can be hidden. So they dislike water. So what happens is that, Kevin, what happens is that those proteins will want to hide from water. And by hiding from water, they interact with each other and they form stable quaternary structures. So sometimes the quaternary structures are stabilized only by hydrophobic bonds. Sometimes if there are free sulfide groups somewhere, they can get close to each other and also be stabilized by disulfide linkages. So it depends on the protein and the composition of the protein. Now, casein, it's not plant protein, but it does have high degree of hydrophobicity extent, especially beta casein, very hydrophobic. And also they are phosphorylated. So they start forming protein-protein interaction via calcium phosphate bridges. So then they start clustering. And the kappa casein comes and fills the surface with this glycomacropeptide that is negatively charged. And then your casein micelle is stabilized in the milk. So that's a quaternary structure of the protein. Another form of quaternary structure is your collagen. So they form strands. Why do they form strands? Not globular. There are strands. Why do you think? Structure of the protein, it's open like that because it doesn't have high degree of hydrophobicity. So you don't see that protein want to just fold on itself. So they have a lot of polar amino acids, and then they are stabilized like that by hydrogen bonding, and sometimes also disulfide linkages. But then they are fibrous structure rather than globular structure. This is a quaternary structure that is globular. This is globular. This is fibrous. So those quaternary structure are impacted a lot by environment. But what's in the environment? Any changes in the charge, presence of organic solvents, in casein, try to take the calcium out, the whole micelle collapses. So they are really influenced by the environment, and that's what we call, later on I'm going to introduce association, dissociation. The quaternary structure, they can associate into quaternary structure, and they can dissociate depending on the environmental conditions. So this association and dissociation, we don't call it denaturation. So the association and the dissociation of the quaternary structure is another form of denaturation, but not really denaturation. It's reversible. Unless covalent bonds are formed, it's not so much as reversible. But usually those associations are reversible based on the environment. Denaturation, mostly when we talk about denaturation, we're mostly referring to the tertiary, secondary, and primary. How can a primary structure denature? Enzyme hydrolysis, you break the peptide bond. So now you denature the protein on the primary level. So actually enzymes can denature protein on tertiary, secondary, and primary. Because once you start breaking, chopping off that protein, you are disrupting a lot of different bonds. Okay. Go ahead.
As if it's possible with like a very large protein that doesn't have many hydrophobic part in the surface. Is it possible that it doesn't form collagen?
Large protein. I don't think there is in nature a very large protein that doesn't form a quaternary structure. Yeah, I can't think of an example. Yeah, mostly like if you take plant protein, there are large proteins and they form very large quaternary structure proteins. And whey protein, they're very, very small proteins and they don't form quaternary structure. So I can't think of an example where you have really big protein and sitting by itself. Yeah. Also, I will talk about I will talk about that later. A concentration of protein in solution impact their interactions with each other. So if you have a really large protein, but it doesn't exist alone in the solution. There will be another large protein, so you are decreasing the distance between them when they're very large, then you are bound to have protein.
At the secondary structure, it's stabilized by hydrogen bonding. And do both the R groups and nitrogen participate in that hydrogen bonding? Okay, so you can like categorize which one like participates, like they both.
They both, but mostly the R group, because your terminus carbon dioxide and amine group, they are actually independent. So you only have carboxyl group carboxyl N and amine group P. So what's inside are your R group functional groups. Yeah. Yeah. Yes, I will cover it when we talk about legume protein. They are very good at associating with circulating. So, for example, soy protein, one part of it, there are multiple fractions, but legume protein, it's a hexane. So it's made up of 6 monomers. So, and they form, first of all, they form a trimer, and a trimer interact with another trimer. So the 2 trimers are interacting via hydrogen bond. But then you have, within the trimers, they're interacting via ionic hydrogen bond. Change pH, change salt, you can disrupt some of those interactions. And then we dissociate them into 2 trimers. So under different conditions, it exists at hexane. Or monomer, or subunit of the monomer. I have a whole figure that will come. Yeah. My phone. I can't silence. This is my glucose sensor. Sorry. Okay. All right. Say that again.
Any kind of changes in structure where doesn't have protein in activation, doesn't have to be linked or doesn't have to.
Yeah, protein can be nature because of like its pH. So you would have like charges, but then you disrupt the ionic interaction within the protein, and it will. So extreme pH, extreme salt for extended period of time, heat, physical like cold plasma. So we're going to give a lot of that. A lot of things can break the code. Enzymes, reducing enzymes, organic solvent. The sky is the limit. Proteins are very sensitive. Like okay. So examples of quaternary structures other than casein and soy and other legumes, proteins, we have this is the hemoglobin. So it is made up of 4 polymers. And then this is the collagen, which also strands of individual proteins that are interacting via hydrogen bonding and potentially disulfide. So fibrous, intertwined, or they can, like collagen, but they can also be intertwined with small proteins aggregating with each other into strands, like actin. Usually fibrous protein act like structure protein, so that's the meat structure. That's what we try to imitate with plant protein. It's very hard to imitate. And then you have your globular protein. All enzymes or majority of enzymes are globular, and all of functional plant proteins are globular. So now the composition of the protein. So we have homoprotein, that means it's only made up of amino acids. There's nothing else in that protein. But we talked a little bit about proteins being phosphorylated, like alpha and beta casein, glycosylated, like the kappa casein, also visilin or chondroisin in soy and P, they are also glycosylated. So these are other examples where the protein is covalently linked to a carbohydrate. So both of these play a role in the stability of the micelle. The phosphorylated protein form calcium bridges, these blue dots, and the glycosylated protein form this stable, negatively charged components on the surface of the micelle. We have the lipoprotein, which makes those protein great emulsifiers. Okay. So, like each amino acid, they carry a charge at a particular pH. The whole protein carries a charge at a particular pH. And the charge, we refer to it as net charge. We refer to it as net charge because you have a lot of charges in the proteins. You have positives and negatives at all sorts of pH. But when you add them together, you end up with a net charge. So the pH at which your net charge is 0, so that is the isoelectric zone. As you titrate with an acid, your carboxyl groups start picking up hydrogen, so you lose negative charge, so that your net charge will be positive. As you titrate with the base, your amine groups start giving you their protons, and then your positive charges decreases, then you end up with having that negative charge. That's the theory behind changes in pH. So when you have a net charge, the higher is the net charge, the more the repulsion is between the protein, the more soluble the protein is going to be, or more interaction with water. The less charge there is, so you induce protein-protein interaction via ionic interaction when you plus and minus will interact, but also what drives them together when there is not enough repulsion is the hydrophobic component on the protein. So you have two proteins, you have hydrophobic components on the surface, and then you don't have net charge, so there's no more repulsion. So the hydrophobicity is going to bring them together, and that's why they precipitate the diaphragm. That's a big part of it, is the hydrophobic pull, because you lost the repulsion. That's why when we do characterization in our lab, we do surface charge, we do surface hydrophobicity to understand the impact on different functionalities. So changing the pH will impact the net charge. Adding salt, how would that impact your net charge? What happens when you add NaCl? There's other salts as well. With NaCl, they are dissociated in water. So you have Na plus and you have Cl minus. So what happens? They shield the charge. It depends on the concentration of the salt. We're going to talk about that later. Sometimes a little bit of salt adds, we'll call it charge load. Increase the charge load on the protein and you'll get salting impact, if you've heard of that term. So that means you have a little bit more charge on that protein and you have more interaction with water. But if you dump a lot of salt, so the Na will react with negatively charged groups and the Cl minus will interact with positively charged groups. So you start shielding charge. And also salt will compete for interaction with water. Then you lose solubility. We're going to talk again about salting in and salting out effect. So it's all has to do with how they impact the charges on your protein. Okay, let's see how much you remember your amino acids. If you have a peptide that has 5 residues of lysine, 4 residues of arginine, 6 residues of aspartic acid, and 7 residues of glutamic acid, and 11 residues of glycine. What would be the net charge at neutral pH? of that peptide. It's not a real protein. I just made it up, a peptide. Huh? What? Negative what? -4. Yes. So you have 5 residues of lysine that's positively charged, 4 residues of arginine that's positively charged. Both are basic amino acids. So now you have +9. But then you have 6 aspartic and 7 glutamic. These are negatively charged. So that's 13. And glycine carries no charge at pH 7, so -4. That's just to illustrate that when you say net charge, it's adding all your charges and what ends up being the total charge. Okay. So I added these slides last time I taught the class because later on in the semester, is this always showing on the top? Huh? Okay. So later on in the semester, you'll hear me refer to classification of proteins. You're gonna hear 2S, 7S, 11S, 15S. What does that mean? And you're going to hear albumins, globulins, cholamins, glutalins, and you're going to hear me say globular, flexible, open structure, fibrous. So we really need to talk about these different ways we classify proteins so that you're familiar with them as we go through. Doesn't want to advance. Why? Okay. All right. So classification based on shape. So you have your globular proteins. Soy glycinin protein is globular and forms a globular quaternary structure. So the monomers are globular and the quaternary structure is globular. Bovine beta casein is an open structure, flexible open structure. So it doesn't have organized secondary structure, like we said, because of the high proline. And this, I think we talked about having high percentage of hydrophobic amino acid. That's why they fold and form globular. And then the fibrous ones, they have high percentage of polar amino acids. And stabilized by hydrogen bonding or disulfide. The other classification is based on Osborn fractionation. So they named the protein based on what the medium they are soluble in. So albumins are soluble in water at close to neutral pH. Globulins are soluble in dilute salt. Prolamins in 70% ethanol. Glutalins need like either high acidity or high basic solutions, and sometimes you add reducing agents because they usually form disulfide linkages, stabilized by disulfide linkages. So you want to solubilize them by breaking those disulfide linkages. So examples of these proteins, albumins, mostly in plant proteins, albumins are mostly enzymes and enzyme inhibitors or cofactors. But if we talk about animal-based albumins, example is alpha-lactalbumin and egg ovalbumin. They are soluble in water. Globulins example, there's so many different globulins, but example is P-vicillin, soy glycinin. You will hear about those a lot later on. Prolamins, of course, you're familiar with wheat gliadin. And then cornzein is also a prolamin. Glutellins, wheat glutenin. So this says glutellin with an L, but wheat glutenin is part of the glutellin, but sometimes some literature, if you read it, they refer to it as a prolamin. But it is really the true nature of it is glutellin because of its solubility categorization. The other glutellin is sorghum glutellin. Sorghum doesn't have glutenin in it. It has glutellin's type of proteins. Okay, the other classification that you will see some of the plant proteins are classified like that is based on the sedimentation coefficient. And the unit is Svedberg S. So what it is when you ultracentrifuge a protein, the speed by which it precipitates refers to that S. So the bigger the protein, the slower, or the faster, sorry, the faster it will sediment. The bigger protein, when you ultracentrifuge, it will sediment fast. So it will have higher VAG. So bigger proteins are associated with higher sedimentation coefficient, but they're non-linear relationship. You can't have 7S protein linked to 8S protein gives you 15S protein. It's not like that. It's non-linear relationship. So historically, who started it is soy protein because we know a lot about soy protein and specified it before other plant proteins. So it was commonly used for soy proteins. So trypsin inhibitor is an albumin, and then you have the 7S beta-conglycinin, 11S glycinin, and then sometimes you have larger molecules forming depending on the environmental factors, and they have the 15S. But later on, we started referring to other proteins with 7S and 11S from different sources, not just soy. So 7S, we also have the lupin, beta-congluten, chickpea vicillin, or even pea vicillin, and other types of 7S-like proteins. 11S, you have pea legumin, soy glycinin, canola cruciferin, so hemp edestin. So we have 11S in different types of or sources. Well, we end here. And then I'm going to, well, you're super excited. I'm really good to reach that. I finished that. Okay. All right. So we'll go to the next one. Before we get started, let's unwind a little bit and have you chat with me. First of all, do you want to say? You guys don't want to do it. All right. Okay. So here's a question for you. I want each one of you to think of a protein analysis that you have done or wish to do or know about, and tell your group what is that. So it could be a measurement, it could be a characterization essay, it could be a separation, something you had experienced. So take a moment, think of an example, and we'll go on with it. So you're going to educate each other what I'm going to talk about later. Okay. Think of a good example and a good way to explain it to your colleagues. Challenge. Okay. Even though you're not officially registered, you will be asked. Okay.
'Cause, 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 'cause,
If you're ready, you can raise your hand. You are ready. Okay, go ahead.
Well, you just talked about, Osborne fractionation, so
Mhm.
I usually talk about Osborne fractionation, kind of what I had experience with, because it's kind of unique.
Yeah.
But when I started as an undergrad, I helped Nigel a lot with that. So Osborne fractionation, like we said, is the 4 different types of proteins that are soluble in different things, so the extraction is basically just going down the line, solubilizing the water, centrifuge.
Before you solubilize the water, because you went
Yeah.
there, tell me what you have to do. So
First,
take
you
the
deep
flour. Uh-huh.
First take the flour, then deep fat it in water saturated butanol. Get the fat out, then solubilize it in water, bake it for an hour, centrifuge. Take out the water soluble, and you do that, I think 3 times. And then you do the same exact process with the salt solution, same process
On
with,
what? On the precipitate from the first, right?
from the,
When you
No,
remove
from
the
the top.
albumin soluble, then you have your
yes, you have
precipitate.
to.
You take the precipitate. Okay,
Take that, solubilize it in salt. And then same process, take the precipitate from that extraction and do it in ethanol. And then the final one is like a solution with the BTT and the acetic acid
on the palate.
on the palate of the final one. So long process and it's based on the solubility.
So why are we doing this? Just to make Nigel miserable in life?
So that we can actually look at the 4 fractions versus just the protein isolate using one method.
Okay, so it's specifically Nigel looking at, varieties, 200 varieties. And we were approached by the breeders, they wanted to know which of these varieties have the highest amount of the most nutritious component, the globulin. So in order to determine that, we had to go through and get all of these different proteins out and do a mass balance study and determine the relative abundance of each of these proteins. And this is just a small part of Nigel's work. True.
And then he did on all those fractions.
Huh? Then
Size
what?
exclusion.
Oh, yeah.
So
You want-
fractionated and then fractionated the fractions.
And then he took the fraction, run it on size exclusion. And not only that, took the fraction, each fraction from size exclusion and sent it to proteomics to do the verification of the identity. And that's how you do a PhD. Yeah. Okay, so that's a very good example of what we will be talking about. All right, who wants to go next? Come, don't jump all at once. All right, yes, tell me.
I measure water volume capacity of protein isolate powder. I mean,
Okay, let me ask you this, is it water holding capacity or water flying? Tell me the method and I'll answer that. How do you measure water hold?
the protein isolate is water. And we do it for morning for half an hour. And then
You're measuring water flying.
fine.
Yeah. Mhm. Good. And then how does that help you?
This property can indicate the property of protein isolates. It can impact the temperature after being processed. So.
Yes, because the more water it binds, the more juicy your texturized product is if you're doing high moisture extrusion. So yeah, so what you're measuring is water binding capacity. The water holding, we're gonna cover this later on, don't worry, in the functionality section. But water holding, you are holding water in a 3D network. So in a gel, you hold the water physically in traffic. Water binding is the actual chemical binding of the molecule of protein with the water via hydrogen bond. So that's why. So what you measure is what, and its impact viscosity, its impact the ability to keep the water and the juiciness of the end product. So either viscosity in a beverage, for example, or in the batter of cake or cupcake, or holding that juiciness in actual product. Okay. You want to tell me?
I was thinking, since functionality is also involved, I'm doing the multiplicative capacity.
Yes.
Yeah.
How do you do that?
So we use the conductivity method. So basically what we're looking is like the phase inversions when they work on the protein. This has been the water and the express in milligram protein that's needed. And the protein per
Grams of
Yeah,
oil
oil.
probably per gram flow, right? Yeah. Yeah, we're gonna talk about emulsification capacity later on.
I'm done.
Yeah. Well, Emily, tell me. You're still thinking. How are you, Heidi? I can see you, you're very tall.
I guess like recently, you know, my key protein isolate. Well, I've been trying to like isolate the protein and trying different extraction methods and see if that kind of changes or results in like functional behaviors. So like, I guess right now looking at changing the pH in which we're solubilizing the protein and then changing the, whether or not like thermal functions or not. And so I guess what I found by changing the pH and by thermal heating it is the formation of soluble aggregates, which is probably more functional. Protein. Something that is my.
Yes, actually, you know, the dissociation and the association that I talked about earlier, that's what Medora is trying to work on, determining how dissociation and the association impact by changing environmental conditions as she extracts the proteins. Very good. You want to tell us something?
I was going to talk about emulsification capacity, but
Go on.
I did talk about.
That's
Yes.
about OPA.
Oh. Yeah,
Why do you use it? You don't have to go through the method like step by step. But
As to the-
what are you measuring when you do your OPA specifically?
the percentage of amine blockage.
Mm.
So when I glycate the protein with some type of carbohydrates, they will covalently link together and will determine how many groups were left without linking to any carbohydrate.
Yeah, so that's a way of determining extent of glycation. Because primary amine are most reactive, and then we use the OPA agent that will react with the primary amine. And if we block primary amine through Maillard-induced glycation, then we have less for OPA to react with. And that's how we determine it. Okay, Shri, tell us. So,
I guess like indoors, I've also been making a lot of extraction.
yeah.
Then I guess Andressa spoke about OPA. What else?
No, you know, you're gonna have a presentation on enzymes. So what is so important in your work to control?
To control enzymatic hydrolysis or proteolysis,
Yeah,
because that will, I guess, I'm guessing it breaks it even at the primary structure.
well, not, I'm guessing, it's very true. Yeah, you break down the protein completely while you're extracting your alfalfa protein. You don't want to break it down. So,
Because it doesn't have any functionality,
mm,
it's flavor,
mhm.
and yeah,
So what do you
then
do?
it's isolation.
How do
And
you
so
manipulate?
we thermal, well, I guess we use acid plus thermal, denaturation
Mm.
to inactivate the enzymes. And
Yeah, and then you measure, what do you measure? You made a different thing to determine if it was successful.
Oh, yeah, so you see again, there's one of them. Which will tell us like the extent of,
BCA is a protein.
oh, sorry, OPA.
Okay. Yeah.
That will tell us the extent of electrolysis,
Yeah,
in the protein.
so this case is opposite to Andresa's case. So when we have hydrolysis, we have more free amine, more primary amine, so you have more interaction with opioid. So it's an opposite effect for the two reactions. One you determine percent loss, and one you determine how many peptides you broke to get the degree of hydrolysis. So that's one. Okay, we're gonna talk about that. Yeah, go. You should have taken the class for credit. What are you doing? You're not paying for AM. Okay.
No. So what I actually that I'm not doing, but I used to do a lot that is general.
What is it? Zelda?
Yeah.
Ah, okay.
Yes, that is general, Taylor method, that is the dilution, distillation, and then titration.
Why not this one? Why not this one?
We didn't have that before. No. When I did my master's, we didn't have people. So we
Okay.
had, they used to say that it is the best in not available, but anyway. I cried a lot because we were making, so my project was on making hydrogen ice cream. So I always were like, making my fingers crossed that the 10% or 12% am I getting in the final formulation or not. In the last moment, I get to know that whether it reached or not. And then when I started working, again, the same thing. We were trying to make high sports nutrition product. There is also like I'm standing in front of the unit, temperature unit, that whether it went above the level claim or not.
So tell that. So I think you and I have something in common. Crying a lot in master, I've done a lot of Zelda during my master. It's a very long process.
Very long.
I don't know which equipment you had, but in my
Yeah.
my
It takes a lot sometimes, but I mean, we got habituated. I put 4 hours. I know it is gonna take 4 hours for digestion and then distillation 1 hour.
yeah, and then titration.
And then titration.
Okay.
And the breakdown very often.
Okay. What else? Let's see, you tell us. What did you do with your stinky, smelly air protein?
No, not a lot, but I guess like the characterization I was involved in is a lot of gelling, especially like meat alternative thing, like you need gelling, because a lot of the plant-based are very soft. So yeah, you just like make a slurry, I think we use like 20%, 25%, and heat it 95 degrees C, 30 minutes. It makes gel, you measure the strength, you like constant strength. So,
Pretty much what we do now. Okay. And did you gel?
no.
That's very sad. So you never got to texture analyze your bit.
Yeah.
Okay. You felt already. No, you didn't. Okay.
The only
What are you
things that I
waiting for?
use. Now, the investigation and the phone, well, but, the degree of penetration that I, now I know, by the HPLC.
So what do you determine by amino acid composition?
No, it's based on the native structure of the whey protein. After the heating, of the powder, I reconstitute and the hydration, and after that, the pH, then reach to isometric on the 4.6. And the denatured proteins go to sediments and come back with the casein, if casein was in the solution. And everything in the supernatant. And after that, I centrifuge, and everything that is denatured go to sediment and supernatant, that is a native protein. And after that, I dive into it and inject to HPLC to see that the amount of the heated and unheated, the change of the peaks. Yes, and after that, based on the concentration, I calculate this.
So what size exclusion?
No, is that it's the Zormax, it's a reverse phase. It's a
Reverse phase?
Yes.
Okay. We will talk about chromatographic separation of protein. Let me see, let me see. You
But,
know,
but I heard that the best way is the science solution
huh?
for the
Centrifuge,
figure of the
yeah.
relation.
Yeah, we'll talk about separation based on centrifuge force. Sarah, what are you up to this year? Hi,
We talk about liquid waves something, take time.
Lico? What is Lico? What is Lico? Lico is a brand.
I will talk about solubility.
What's the method?
What
do you
mention?
mention?
Is donuts.
Donuts, very good.
So technically, I guess. So it's like based on like Boston reaction. So technically, I think carbon and sulfide are involved in the reaction.
Combustion, you burn everything up
Yeah,
into
but then
gas.
something combines.
Something.
So yeah, and then you get the nitrogen content, and then you just use the conversion factor. But then it takes you like 4 hours to calibrate and do maintenance, and then like maybe 5 minutes for run. So it's great.
But it's 4 minutes per sample though.
Yeah.
After you
Not 6
calibrate.
hours.
Huh? Okay. Yay, do none. Okay. What have you been up to? No, it's not Rico again. So how do you do solubility?
So, first we have sample and we solubilize it in W, and then we do it into the regions.
Yeah, but after you solubilize, what do? Don't worry about details of pH.
And so we stabilize and then we move it.
Don't worry about heat. Just what happens after you solubilize the protein. You heat it, the pH doesn't matter. You solubilize the protein and then what?
And then, once you, what are you trying to do? We're trying to figure out the amount of protein and whether it's insoluble in the solution or whether it stays in the pellets. So,
So we centrifuge.
Yes.
You solubilize, you centrifuge, you take
Yes, you take supernatant, and then you heat it, and then now you go and
do the doing.
and then, yeah, you go to do this, and then you figure out the amount of protein in the sample.
Yeah, so you determine soluble protein relative to the original total protein, to determine how much protein was soluble. Very good. All right, let's back and leave. No need to talk about any, no. Kidding. All right. Very good, very good. Oh, you didn't share anything?
No.
Okay.
Like a side note, but like if you didn't have do mass, would you have to do alcohol for like solubility?
Yes.
So then.
Yeah. Why do we have to do either Dumas or Kelda? The reason we either have to do Dumas or Kelda is based on determining nitrogen, the specific nitrogen, although it's not, it's crude. Total nitrogen, not all nitrogen comes from protein, but you get the relative. Other methods are indirect. So if you take BCA, which is biosynchronic assay, or Bradford, they all are a specific reaction. So BCA, well, copper ions reduce the cuprous and then they add proteins. What reduces cuprous? Cuprous is reducing amino acids or peptides in the protein. But if you have sugars that are reducing, so they are going to increase the reduction, and you will end up having inaccurate. So, and then the Bradford is a specific reaction, and then you would have to have calibration, and usually your standard is albumin. It has different composition of amino acids than your actual protein. It's not accurate. So if you have pure protein solution and you're just comparing, like you are doing the OPA method, and you're just comparing one sample to the other, then the DCA is sufficient, and it comes from a pure solution that you sedimented every impurity and you measure only in the super. But when you want to determine protein, the best method is the nitrogen. Yeah. So Does that make sense? Not quite.
Yeah, well, I
Yeah,
guess
yeah,
with like with Keldol, you have to put it in like it's like usually like a little say like a solid form. So like the procedure change and like.
You don't have to have all this in the solid form. If you have milk, you just pipette it in, and you don't have to use the fat. Yeah, it's not. For all types of food, you just adjust the amount based on the nitrogen, so that your titration is within the range. So for cheese, you weigh 0.2 grams. For flour, you weigh 1 gram. You weigh 1 gram. It's not micro. It's the regular powder. If it's micro, you even weigh less. Yeah. So you adjust based on the sample. Both Dumas and Keldol, they are universal for all types of foods. Complex. Now, sometimes Keldol is more accurate because it's an amine group. Because amine group is what's reacting, whereas the Dumas is all nitrogen. Something's not amine or not. If you have a vitamin, it doesn't have to have nitrogen in the vitamin. So, but usually these components that have none is really less low concentration in general. Okay, very good. All right. And that is why Pam is always behind. Because I like to ask a lot of questions and have you talk, and I talk. Okay. Okay. We're going to talk about chromatography, but in this class, I don't spend 4 or 5 lectures on chromatography like I would in food analysis. So I will briefly remind you of the different forms of chromatography, but I will rely on you remembering your basics. Okay, so from what you remember, what can we use to separate proteins in solution? So if I have a mixture of proteins in solution, which form of chromatography I can use to separate? Oh, this is back like that? Hey, why? Stop sharing. And then, I don't know why it does that. And then where did Zoom go? Oh, I need to share it. Ah, okay. Thoughts? Huh? A and C. Okay. Any other? All of the above. And more. So this is just, you can use size exclusion, anion, cation, affinity chromatography, hydrophobic interaction chromatography, reverse phase chromatography. Yeah. All right. What about this one? Huh? A and C? Any other? Just A. Just A. ELISA and Western blot, they are immunoassays. So it just talks about whether your protein is immunoreactive or not. It doesn't really tell you what's the MS composition, or sequence, or surface hydrophobicity, or any like particular structure related information. All right, so when we say protein analysis, we don't necessarily mean just quantification. So protein analysis include everything you actually talked about, gave examples about. So can you give, there are three categories. Can you give those three categories of protein analysis? One is the easiest, quantification. Quantification. What else? Function, determination of functional properties. Structure. Let me see if this is correct or I remember wrong. Quantification. Oh, there's separation and purification. Oh, characterization and identification, that includes functionality, structure, identity of the protein, nutritional quality, yeah, all of that. So separation and purification is also a protein analysis category. All right, so good. Now, why? Why do we care? Why do I do any of those? Why would I care about separation and purification?
But you
Or what's the ultimate outcome? Applicability. Where do we care for separation of protein? To produce ingredients, protein ingredients. So ingredient preparation. So we're going to talk about a lot of different methods to isolate proteins using different differences in solubility with the membrane, using, yeah, mostly membrane, and also differences in solubility are different ways to get the proteins isolated. Okay, what else? Why do we care? Mm, yeah, I don't have that reason, but yeah, it's under characterization. But why? Why do we do what we do in our lab? Basic research. We're doing research to understand different types of proteins, characterize them, identify them, see where they are applicable. So basic research. Okay, what else? The last thing. Huh? Yeah, get a PhD and then go to the industry. Yeah, industrial application. So once we're able to produce the ingredient and once we characterize it, then we can determine where best to apply it. Is it best for beverage application? Is it best for extrusion? Is it best for what? Okay, good. Then what I need is, what methods do I use for all of this? Legal methods. We can't go kill anybody to determine if the protein was absorbed or not. We might do it for animals, unfortunately, but not humans. So legal, nutritional, like what I mean by nutritional is like when I develop separation and purification and process it, I want to make sure that the protein remains nutritious. I don't lose the quality of the protein. Safety, I don't use like solvents or chemicals that would end up being toxic and not safe. Economical, everything we do in the lab, we have to determine whether or not we can scale. So a lot of you that work with me on methods of extraction, we try in the lab and then go to the factory. We might do the best science possible to get a lot of PhDs, but if it doesn't end anywhere, it's not adapted in industry, we learn. Maybe that's one thing we benefit from, we learn, but we really don't apply it anywhere. And food science is an applied science. At the end of the day, we can be in the chemistry department and go do all the proteomics in the world to understand different proteins. But for us, it has to end somewhere. Yeah, and functional implications, meaning if whatever method I'm using, it might impact or characterization. even during my characterization, I might induce denaturation that doesn't happen while processing. So my results will be wrong. So if my assays or methods will change the characteristic of a protein, my conclusion will be wrong. So basically my methods need to be well thought through that get good outcome, safe, legal, translatable, translation research. That means translate from lab to scale. Yeah. Okay, questions there? So we measure protein content in many ways. We talked about our wonderful Kelda and Dumas, they're high top. But we have other methods we can use. Infrared spectroscopy, we can do IR for quick protein content when we are doing, quality assessment during processing. We don't have time to for that. We don't have legal because it's so expensive, or it's broken because it's always needs maintenance. So then you end up doing IR, which you need to be calibrated. If you remember from the analysis, all IR methodology needs to be calibrated using official methods of analysis. Now, the research methods, they're all based on measuring absorption of some sort, and they are usually done on pure protein solutions. So with minimal interference from other components. So they are not meant on complex samples. So we cannot get flour and take that flour and do BCA as is. There will be a lot of interference and we will never get the accurate reading because it's not only interference with the reagents. When you measure absorption, you might have other components in your sample that might absorb at the same wavelength. So these are research methods. BCA is very common. We use it in the lab. Bradford is another one based on binding with a dye. And UV absorption is very commonly linked to chromatography. So when we are doing chromatographic separation, we often look at our protein distribution using UV absorption. PDA, photodiode array, or variable wavelength detector. The others, Burette and Lowry, are different versions of assays that are also based on reducing power. So these are the methods, but why do we care about measuring protein content? Can you give me an example where measuring protein content is important? Label, very good, that's very big, important. Quality in what way?
For making a protein isolate, and you think it's supposed to be 85, but it's 80.
Exactly. So measuring our protein purity in our ingredients. Very good. What else?
Check the functionality of the.
Exactly. When you're doing your EC calculation of emulsification capacity, you really need to know your protein content to calculate grams of oil emulsified per gram of protein. So determining functionality, we need the protein content. That's why in our lab, we always measure protein content. Then we do the functionality because we assess based on the protein content. Okay. What else? Is there anything else? With enzymes, why do we care about protein content? What's
Determine how much they can.
so what? What I meant is like when you measure enzyme activity, usually it's per gram of protein. So when you're measuring biological activity, you want to determine it per gram of protein. So here you are. So everything we talked about is there. You want a minute to write it? Huh? Do you have it? Well, I don't put it, so how else I'm going to ask you questions, and how else will you answer me if it's right there in front of you? And then when you write it, you will remember it. But take a minute, write it. Put your heart into writing it. Okay. See, it gives me a break also to stop talking. You're right.
Maybe a silly question, but like, when you have quality control there, are you talking about just research or like in industry? How would you measure the protein content?
Oh yeah, so quality control basically, you are milling flour, and you are before you mill your wheat sample, you are removing the bran, and then at the end you get your white flour. So it should have a certain protein content to verify that you actually removed, instead of going with fiber content. For instance. So on the line, as it's coming out of the mill, you take a sample, you put it in the IR. Okay, cool. You got 12% protein, you're good. If you get 13% protein, not really expected. Yeah. Okay, good. All right. So now this you are going to memorize. No, you're not going to memorize. It's a reference table. It's basically giving you all different types of methods of analysis and the principles. So I want you to, high level, know the principle. As a graduate student, you really need to know what Kellogg does and what demands. So, but I wouldn't expect you to know like details or to memorize sensitivity. Okay, but it would be good to know that what is destructive and non-destructive. So obviously all methods are destructive except the absorbance, IR and absorption. Yeah. So this is kind of summarizing what you have learned as an undergrad. Okay. Oh, also on Canvas, where you find these slides are week 4. In that week, you will see supplementary reading material. So if you want to learn about anything in more detail about the method, it will be there. It's like, we don't have a good book that contains everything about it. So that's why I put reading material to supplement your learning. Okay. All right, here we go. You can start writing because the next slide is not in your. Okay, so what is protein separation utilized for? You kind of said it earlier. Why do we care about separation of protein? To produce ingredients. Okay, what else? Why do we also do all these purifications sometimes in the lab? All of this size exclusion chromatography, followed by collecting fraction. What are we trying to do? Characterize. So for research purposes, we need to understand our protein, especially when we have new protein that we're trying to discover or determine its functionality. We really have to purify and study it after we purify it. And especially if we want to determine the sequence or the origin, you need it to be as pure as possible. Yeah. Okay, what else? A big part of isolation and determination is to determine the impact of processing or breeding or what have you, impact of upstream, downstream on your protein. When it's present in a complex matrix, you can't study it very well. So you want to take it away from everything else in your sample and then determine how different things impacted that protein. So it's the last one, and not just processing, I would say upstream and downstream, yeah, across the value chain. Huh?
Denaturation.
Not only denaturation, yeah, well, denaturation, but what exactly happened to the protein? Sometimes denaturation is at different levels.
Yeah.
Denaturation can include hydrolysis, can include tertiary, can include polymerization. What is it? What exactly happened? All right. So we want to separate the protein, we want to isolate it, we want to purify it. How? How do we do that? We really need to know protein characteristics in order to determine how to do it. So we know that proteins differ from different sources, different in nutrition, different functional properties, but we don't care about those for separation. We know that they differ in biochemical characteristics. So what are these biochemical characteristics? So their solubility under different conditions, their thermal stability, the size, like how big the protein is, the configuration, is it tertiary structure, is it an open structure, is it quaternary structure? Charge, what charge does it carry at different pHs? Absorption characteristic, if we want to use chromatography, we want to know what chromatography would it work best with based on its absorption characteristic. And then biological affinities to other molecules, especially if we are trying to purify an enzyme. If we know what that enzyme is, we can use specific enzyme inhibitors, let's say, and put that in the column so that we can get that enzyme out. So what influence these biochemical characteristics? Of course, the composition, that means amino acid composition to be specific. And not only the composition, the sequence, where each amino acid comes in the sequence, and then the number of amino acids. So how big is the protein? You can have 180 amino acids, you can have 1,000 amino acids in that protein. And then the configuration, basically the structure, open, closed, globular, tertiary, quaternary, all of that. So these characteristics are impacted by those, and the result would be completely different protein. So whey protein, casein protein, different structure, different functionality. So, but because they have different structure, we need to isolate them differently. So different biochemical properties, and to purify casein is completely different than purifying whey protein. And if we want to purify plant protein, like this very complex hexamer of soy, also another different set of properties that we will utilize to isolate that. So when we want to choose the method, we know characteristic about protein. Okay, we know soy protein can be soluble at pH 7.5 or 8. We know that. But what other characteristics I need to consider before I start choosing my method? To purify, to isolate, what do I think of? Other than the type of protein, what do I think of? Type of protein, yeah, so other than knowing the size and configuration and amino acid and solubility and all of that, what other consideration I have to think? So if I start with soy or if I start with pea,
Matrix that it's in,
huh?
the matrix that it's in, like, is
Maybe-
there fat? in there?
Uh-huh.
What
Uh-huh.
else is in there?
The makeup of the sample. So soybean, I have to use that. I cannot extract, isolate protein before removing the fat, whereas we have less than 50% fat. We don't have. So the matrix of our starting material will take into account the matrix when we decide on method of separation and purification, nature of the sample. All right, what else? Do I do dry fractionation or wet isolation? What do I consider? How do I choose? You know, dry fractionation, you cannot get it over 90% purity. So the final purity that I want, do I want 50% purity of my protein ingredient? Do I want over 90% purity? Do I want 100% purity? Only protein, nothing else. So the purity of the sample, and then what else? When you are devising your method, what would make you choose pH 8 versus pH 12? You know that pH 12 is going to get that protein soluble. Why won't you go with pH 12? Huh? Harsh for the protein. We have to think about conditions that doesn't really damage the protein. So yeah, so when we consider separation, we don't want to damage the protein. Okay. Remember what I said about our food science world? What's the last thing and most important you want to consider? What's that? Application, feasibility, cost. Can we do this in industry? Can we scale the method? Is it cost effective? So here we go. Time to write. Okay, very good. Now we know what we need, those special consideration, nature of the food, matrix that I'm starting with, or the sample matrix. What the extent of purity I want, maintaining the stability of the nutritional, biological, functional properties, and industrial scale, feasibility, cost, etc. Okay, so how do I monitor effectiveness of my isolation? Emily? Hi. How do I monitor effectiveness of isolation? You went into the lab and you worked with someone and you isolated all of these soy protein isolates, day and night dialysis. Then what do you do? How do you determine your success? Simple. What's the first assay you learn? Vico. What does that give you? And year. So the way to determine the success of your method, did you get the purity that you were after? And how much protein you were able to get out of your original sample? Were you able to get most of the protein out or just 20% of the protein? That would not be effective. That would be throwing out a lot of material if you only get 20% of the protein. You will get co-products and you have other waste issues to work with. All right, what else? How do you said amino acid, right? So you determine, well, not necessarily amino acid, I wanted to say composition. You get your isolate or concentrate and you want to see what's in it. So you have this much protein, how much salt do I have? Isn't that painful when we do the ash content and it's above 5? What do I tell you when it's above 5? Go dialyze more. So remove that ash because it will really hurt the protein functionality. So we do that composition analysis, mostly your protein and ash. And then what else do we do after we produce that protein? Now you have it, you're successful, you got most of the protein out, you have the purity that you want, you have low salt content, and now what? Huh? What's that?
Structure.
Yeah, structure. Characterizes structure characteristic. And if we're interested, depending on the interest, what are we interested in? We determine functionality or application and so on. There's one more important thing. Actually, there's so many. But one important thing as well, when we think about food, we put it in food. So we care for nutritional quality. We care for, we didn't destroy the protein, it's still digestible. We didn't destroy essential amino acid, it still has high amino acid score. So all of that is important. Ah, look at taking a picture. Fast and easy, but you won't write it down and then won't remember. Okay. You got it? All right. So this is a summary table that talks about the different stages of purification. First of is removing it from the complex matrix. We call it extraction. Not always solubilization, because sometimes it's not just based on solubilization. It's just removing it, separating it from the matrix. But when you remove it from matrix, it might not be completely in pure form. It might have other things. That if we are solubilizing the protein, it might have sugars and other components in it. So if I want to separate it from solubles, precipitation. So precipitation can happen by adjusting the pH to the isoelectric point or dumping in a lot of salt that causes the protein to salt out. Another separation technique is membrane. It's very commonly used in the weightlifting world, and we will talk about that. We are starting to use it in the plant protein work as well. Ultracentrifugation, I see you using the ultracentrifugation downstairs quite a bit. I've used it a lot when I was trying to separate an enzyme from milk matrix. So the ultra separation in that case separates the casein from the soluble whey. Chromatography, all sorts. Size exclusion, ion exchange, reverse phase, hydrophobic interaction, affinity chromatography. All types can be used. In industry, it is used. They use ion exchange chromatography, especially anion exchange, for production of whey protein isolate. Agripor uses this technology as an example. Okay, so this is a good summary table to study from. So if we look at plant sources, there are two main ways of separation of proteins from a plant matrix. We call it dry milling, and it's very common for pulses. So pulses such as peas or chickpeas or even dry bean. So what happens is you put your hopefully dehulled pulse bean, whatever it is, and then it goes through an air classification system where it gets milled and separated based on density. So the light fraction will be your protein fraction, and the heavy fraction will be mostly starch and fiber. So you end up having two fractions ideally, one heavy with your starch and fiber, but still has some protein, and one light with maximum 60% protein. The rest is also starch and fiber. So this gives you an ingredient we call a concentrate with minimal damage to the protein, because you don't have you don't have wet processing, you don't have thermal treatments, you don't have changes in pH or salt. So minimal damage, basically. But the purity is low. And oftentimes in some application, you want higher purity. In order to have higher purity, we go to wet milling. Wet milling meaning you get your starting material, you add to it aqueous, and then stirring and extracting and going through a process to get to an isolate that has above 80% protein purity. So the extraction usually done at alkaline pHs and precipitation at the isoelectric point. So sometimes it's 4.5, sometimes it's 5, 5.5, depending on the source of protein. We also can do salt solubilization followed by salt precipitation. So we put just a little bit of salt to enhance. Remember globulins in your Osborne fractionation, these are the functional proteins in plants. So a little bit of salt will extract them out. But then we need to get them away from other solubles. So you put in more salt to precipitate them, but this is not a good method. You won't find anybody in industry that uses it. Why? You don't need to the protein, but what? It's expensive. Water usage. It's just a lot of, you want to get rid of that solvent. So it's a lot of water and energy use. So it's not. Now, what we're trying to bring into the industry is salt solubilization coupled with membrane filtration, where you get rid of the salt by diafiltration, ultrafiltration. It's expensive because membranes are more expensive, but it is doable. They use membrane filtration for whey protein. So it's doable. They just have to be convinced that you get better quality protein if you do mild salt concentration and membrane filtration. No pH, no heat adjustments. So oh, I didn't tap forward to show you the solubility of plant proteins usually follow a bell shape. So if we have alkaline above 7, we solubilize most of the protein. And then we use the isoelectric point to precipitate them and separate them from other soluble. And this is the salting in, salting out that I was talking about, visualizing it. So you add a little bit of salt to enhance water protein interaction, and then you add a lot more salt to precipitate. But since this is not a good approach because of the more water use, we use membrane filtration to retain the protein and get rid of the small molecular weight components, and also concentrate at the same time because water can go. So, all right. Okay, I guess I'm gonna stop here, which would be a good stop. We'll finish next time. All right. Come with questions so that I don't always, I'm talking. Even if we never finish lectures, it's okay. Less to study. Waste my time. No, just kidding. Ask questions. All right, you guys, have a great evening.